Hello, everyone. So in this lecture today, we're going to be discussing different techniques to study networks, to model them, and in particular, whenever we want to optimize the performance or some metric of interest in these networks. So in particular, I'm going to be discussing networks mostly from an infrastructure perspective. So literally, we're going to be thinking about networks that we use in a day-to-day basis whenever we want to literally move, let's say, from one place to the other. So that will be a transportation network, or if we want to have electricity in our houses or our businesses, we are going to be using the power network. Water network precisely is the one that moves potable water or sewage as well. A common aspect from all of these networks is that you're going to have some sort of commodity moving through them, and also that these networks are going to have some finite capacity. So you're going to have a maximum amount of commodity that can flow through those networks. So as I mentioned, infrastructure is very general. So that includes energy, transportation, water supply management, and even communications. So in this case, information itself could be seen as one of these networks that I was discussing where the information itself is going to be that commodity flowing. Now, the thing with these networks as well is that they're subject to different events that may disrupt their performance. And one of them that I'm sure most of you are familiar with is natural disasters. And it is critical that stakeholders like governments and literally managers give top priority to mitigate the effects of those disasters. So just in the last few years, we have seen many disasters affecting infrastructure networks with a very large impact to human lives, well-being, and economy. So just if we were looking to just observe the effects of six of these very large events in the past, the effects of those regarding the economic losses would be more than $260 billion. And this is just a few of them. So, and the other issue is that these are growing and becoming more and more often, these events. So we need to be able to quantify the performance of the metrics of the networks. We need to make sure that we can actually optimize that performance. And finally, we would like to take into account the likelihood of having one of these disasters or a disruptive event so that we can prepare those networks to handle those better. So in this problem, there are going to be different challenges. So one is the actual modeling of the networks. What do I mean with this? How do we want to model the networks? How are you going to take into account the different constraints associated with the actual network that you're going to be modeling? As I mentioned, you're going to have some capacity. So how are we going to model that? How are we going to model the commodities flowing through a network? How are we going to model the balance constraints? Because commodities cannot just disappear whenever they go from point A to point B. So yeah, so we need to really make sure that we know how to model that. And for that in particular, today, I'm going to be discussing methods based on linear programming and mixed integer linear programming. Now, there are some other challenges. So whenever you have large scale problems, you really need to be careful about how you model your networks because these optimization models may become very challenging computationally. And third, as you may imagine, uncertainty is an important aspect of this type of problems, especially when you're talking about disasters. You don't know when these are going to hit. So if you really wanted to study this, you would have to include uncertainty into your optimization models. But today I'm going to be centering mostly on the network aspect. So of course, ideally you want to have the three of them, but we're going to start out how to model the networks. Okay, so that's what we're going to be doing right now. So there are different techniques out there to model the networks. It is going to depend on what you want to study in your actual system. It could be as simple as just measuring and assessing the connectivity in those networks. You may want to evaluate distances between, let's say, 2 points in the network. Whenever you want to use a transportation network, you want to travel as fast as possible. So you're looking for shortest paths. But also you may want to go an extra step and you would like to study the actual flows in your system um, as a function of the capacities or the costs of using that system. So for that, we're going to be talking about network flows models. And the most common in that area, you're going to see two very, very often in literature. One is what we call the minimum cost flow problem, and the other is what we call the network design problem. So let's start with the minimum cost flow problem. So the minimum cost flow problem, the first thing that we're going to have is a network, right? And it's going to be direct. So that's the first assumption. Second is that we're going to have a set of nodes. So in this example, you see you have 6 nodes and a set of directed arcs. Okay, so in this case, you're going to have 8 arcs. Once you have this, you need to make sure that you have some parameters associated with this network. So one, you need to have a cost associated with the unit flow through each of the arcs. Okay, so it is Cij, meaning the cost of moving one unit through arc ij, okay, where I and j are nodes in my network. And here, just for the color code, I'm putting this in black, is the first value here in this array. Now you're going to have two other parameters. One is going to be a lower bound for the flows, and the other one is going to be a capacity or an upper bound for the flows through each of the arcs. So this is really important. So the worst case scenario, let's say that you're moving water. So at least you're going to have 0 water flowing through there. What do I mean with this? You will never have negative water flowing through a directed arc, right? If you actually wanted to model the direction, then you have to have two arcs, one going in one direction, one going in the opposite direction, okay? So the same with, let's say, traffic. You're studying the flow through a road, and you know already the direction of that road. So you shouldn't have any flows that go against the direction of the road. Okay, so a minimum bound, in this case, the lower bound would be 0. But there are some other cases that actually you shouldn't have a lower bound 0. You should have something that is larger. I'm going to bring water again. Usually in water, you want to make sure that the flow of the water is constant and is fully pressurized, so you have enough pressure in the water system. Because if at some point you don't have enough water flowing through a specific pipe, that may be contaminated and you may actually suffer in your entire system. So there's a constraint that you need to guarantee a minimum flow of water throughout all the pipes. Okay, so in that case, that would be a lower bound capacity. As you can imagine, that's the maximum that you're going to be able to handle. Now, we need to know how much is going to be the supply or the demand of each of my commodities in the system, okay? So in each of the arcs, we're going to be assuming that you have either a supply or a demand of commodities. So in this case, we're going to be calling this supply or demand as B of I. In other words, the parameter B is going to depend on the node I. If this parameter B of I is non-negative, so meaning pretty much, or actually greater than 0, if it's greater than 0, the node is what we call a supply node. If the parameter is less than 0, strictly less than 0, then the node is what we call a demand node. It's going to be absorbing commodities. And then if that parameter is equal to 0, then that node is what we call a transshipment node. It is not keeping any commodities at all. It's receiving nodes, but it's sending them out as well. So for the basic structure of this problem, we're going to be assuming that the sum of all those parameters over the entire network is going to be 0. What does it mean? That means pretty much that your network is balanced. Okay? So you cannot have more supply than the demand, and vice versa. You cannot have more demand than supply. Okay? So in this particular case, the assumption here is that node 1 is going to be supplying 5 units of this fictitious commodity that we're modeling. Then node 2 is going to be supplying 3 units of that fictitious commodity. That doesn't mean that it cannot receive commodities. The only thing that this tree means is that the net amount of commodities leaving node 2 is going to be 3. Okay. And if you look at node 6 now, is -8. That means that the net amount that is going to be arriving at node 6 is going to be 8 units, 8 commodities. Okay, so what is the objective here? So as I mentioned, you have cost, lower and upper bound. Now we really want to know is what is the minimum cost flow configuration associated with the system? Or in other words, what is the distribution that would comply with all the constraints that we have that would minimize the cost? Okay. So for that, we're going to be defining a decision variable xij that is literally the flow that goes through each of the arcs. And the mathematical formulation, then simplified, would look like this. So you're going to be minimizing a function of that x that is equal to the sum over all the arcs in your system of the cost of the flow through each arc, of unitary flow through each arc, times the actual flow through that arc. Okay. Now, what are the constraints? As I mentioned, so you're going to have some flow balance constraint. So in this case, what you need to make sure is that whatever is leaving minus whatever is entering a node is the net supply that you said you're going to have. And that's why this B had to be positive if you are a supply node and negative if you are a demand node. If you're a supply node, then this part is going to be larger than this part. If you're a demand node, then this part, which has the negative sign, is going to have a larger magnitude than this one. And of course, if you're a transshipment node, then these two are going to cancel out. And what you're saying is that the total amount of commodities arriving at a node is exactly the same as the commodities leaving that node. So they will cancel out. And the capacity constraints, you're going to just say that the flow xij, so the flow going through arc ij, is less than or equal to the capacity of that flow. Likewise, for the lower bound, you're saying that the flow going through arc ij is going to be greater than or equal to the capacity in the minimum flow, the minimum flow of the lower bound through the arc. The good thing about this minimum cost flow structure is that you can use it to model other types of problems. So for example, shortest path, you could study maximum flow problem or transportation problems or assignment problem or even airplane hopping problem. So it's very flexible in that sense. So let's look at some examples. Let's say that you wanted to use the shortest path, calculate the shortest path between 2 points, between 2 nodes in your network. Of course, there are different algorithms that are targeted to this particular problem that are going to be highly efficient, but this itself, this minimum cost flow problem, the formulation, since it's based on linear programming, is going to be solvable in polynomial time. So it's going to be relatively efficient. So you can still use it to calculate shortest path for most realistic problems that you're going to face. So what is the idea again? You want to find that minimum cost of shipping a commodity between a source node and a terminal node. So in this particular example, I'm just saying that you want to go from 1 to 6. So how can we use the minimum cost flow structure for this problem? Well, I'm going to say that this node 1 is going to be supplying 1 unit of commodity. So let's say that's me, right? So I want to travel, so I will be a commodity. So I'm going to be, sorry, all of this. I'm going to be leaving from this node. And then here, the node 6, this is the terminal node that I want to start in this particular case. It is going to have a -1. So it is demanding 1 commodity. It is demanding me in this case. I want to arrive there. Since I'm not going to be staying at any of the nodes, I'm just going to go through those nodes. Then I'm going to be calling those transshipment nodes. So that means that the B associated with those nodes are going to be zeros for all of them. Okay. Now, lower and upper bounds, they're going to stay similar like the idea, except now that in general, the basic formulation for shortest path, you're going to have simply a lower bound of 0, meaning that if you don't want to, you don't have to go through an arc, okay? But a maximum flow of 1, meaning that you can only traverse each of the arcs once. Okay? And the cost here, the cost is going to be the cost that you had from before. And in general, the cost may represent the actual distance between two nodes, or may represent literally, let's say, the cost of a toll or some other type of cost, maybe a time that it takes to go from that pair of nodes, okay, to traverse each of the arcs. So once you have all of that, if you see, we're using exactly the same parameters that we have from the minimum cost flow. It's simply that we're making sure that these values actually are the ones that we're using for the minimum cost flow, and you would just solve exactly as the minimum cost flow, and you would get your optimal path. Okay. Second example, so the maximum flow problem. In this case, what we want to find out is what is the maximum flow that you could send between a source and a sink. That's it. So assuming that your source node is still node 1 and your sink node is still 6, you want to determine what is the maximum flow that you can send from 1 to 6. So how do you do this? Using the minimum cost flow problem. So here, the assumption is going to be that through all the nodes, right, you're going to have a net amount of commodities of 0 going through each of the nodes. So what do I mean with this? If you enter a node, you have to leave that node. That's it. So that's the assumption. So pretty much B of all commodities is going to be 0. That's the first thing. And second, you need to create an artificial link. So that's what I'm putting here in orange, an artificial link that goes from your terminal or your sink to the source. Okay, so why is that going to be? So what we're going to try to model here is we're going to try to push as many commodities as possible from 1 to 6 throughout the regular network. And then as soon as that commodity arrives here, we're going to send it back, okay, through the artificial arc. That's what we want to do. So of course, all the costs that we have here, since we just want to test the maximum flow possible, we really don't care about the cost directly, right? Of the unit flow cost that we were looking at before. So all those costs are going to be 0 now. You see, all of them are 0. Of course, now really important thing to model is the capacity for each of the arcs. So those are going to be very relevant because depending on the capacity of each individual arc, the maximum flow that you're going to have is going to be different. So again, here you're going to have the minimum and maximum flow through each arc. You have to use them directly as before. Now for the artificial link, you're going to have some properties to keep in mind. So what is the cost of flowing through that link? We're going to put an artificial cost here of -1. What does it mean? Pretty much imagine that for every unit that you can send through the artificial link, you're going to get paid. Okay, so that's really what that -1 means. So it's not a cost, actually, you won't be paying, but actually you're going to receive some benefit. Now, what is the minimum flow that is going to be allowed through a link? Is going to be 0. You may not have any flow at all possible, so that's why you have to put 0. But since you don't know how much is the maximum flow of your system, that's literally the problem that you want to solve, then you need to assign here a maximum flow for the artificial link of infinite in theory. And since here we want to actually code this, you are going to put a very large number. Okay, so a flow that you know for a fact that you're never going to surpass. Just to give you an example of how you can estimate that. If you're going to be leaving node 1, it's easy here to see that from 1 to 2, you're going to have maximum flow of 5, and from 1 to 3, you're going to have maximum flow of 8. So just from these two, since these are the only two arcs that you can use to leave node 1, that means that the maximum flow for sure, just by looking at this, is going to be 13. You know that for a fact that it's impossible to have more than 13. So you could put 13 here directly into your optimization model whenever you're coding it, okay? So you would solve this again using minimum cost flow problem with those parameters, and you would find out what is the maximum flow. In this particular case, after you solve it, that maximum flow is going to be 12. Okay. There's another type of a network modeling approach that is called the network design problem. And it's going to be very similar to a minimum cost flow, but now instead of just looking at how the flows are going to be, now we're going to be looking at designing the network itself. So what do I mean with this? It's going to be very similar to what we had before. So you're going to have a directed network with some nodes and some arcs. You're going to have a cost per unit flow, a maximum flow. Here in the basic structure for the network design problem, the assumption is that the lower bound or the minimum flow is 0, but you can always put that as a constraint in your problems. Okay? But in the basic model, you only have maximum flow, and minimum flow should be just 0, and that's it. And you're going to have, again, your supply or demand associated with each of the nodes exactly as in the minimum cost flow. And really the key difference is going to be this parameter f. F of ij is a fixed cost of using or of constructing the arc ij. So that means that before you actually can get to use that arc, you have to pay for that. You have to pay either to construct that, let's say this is a bridge or a road, or just to be able to use it. Imagine that this is a toll, so you have to pay for that. And this is going to be a fixed amount. It doesn't matter if you're just sending one commodity or 10 commodities, that cost is going to be fixed. So the same. What are my variables going to be in this case? Well, you're going to have an amount of flow that is going to go through each of the arcs exactly as in the minimum cost flow problem. But now you're going to have another variable that is what we call a design variable called yij that is going to tell you if you're going to select an arc to be built or not, or to be used or not. So this binary variable, this is going to be a binary variable that is 1 if you actually use it, if you decide to use or construct your arc, and it's going to be 0 if you decide not to pay to construct that arc. What is the objective of my network design problem? Is going to be, again, finding the least cost shipment strategy for my commodities in that network that satisfies all those constraints. Of course, now with the addition of having to decide which arcs you're going to pay to be able to use. Okay. And if you look at the mathematical formulation, it's going to be looking very similar, except for a few key places. So in the objective function, now you're going to have costs not only associated with the flow of commodities, right? Where we had that unit cost per unit flowing there, multiplied by the flow, right? So that's what we had in the minimum cost flow problem. Now we're going to also have a cost that you pay whenever you want to use the arc, each of the arcs. Okay, so we're going to be looking at every single arc, looking if this is 0 or 1. And if it's 1, you're going to multiply by that fixed cost. And summing all of this is going to tell you the total amount that you have to pay to build or to use all the arcs that you wanted to use. The constraints are going to be similar in the sense that you're going to have balance constraint as before. You're going to have now maximum flow as before. But the thing here is that now your maximum flow parameter, U, so your capacity, is going to be multiplied by the decision variable. Why is that? Well, imagine the two cases that you can have. If you decide to build the road or that arc in general, this is going to take a value of 1. So how much would be the total flow that can go through an arc ij? How much would this x could be? It could be anywhere between 0 and this u, right? So that's why we will be multiplying u times 1. However, if y is 0, which would indicate that you don't want to use that arc, you don't want to pay to use that arc or to build that arc, then how much is going to be the flow? Well, it would be less than or equal to u times 0. So in other words, less than or equal to 0. Okay, so you cannot have flow, pretty much is what you will have. Now, there are some other relevant network related optimization problems that are going to be extremely useful to you in many circumstances, and they're going to be using similar formulations to what we just discussed. So assignment problem, that would be one of those. As I mentioned, you could use the minimum cost flow problem to use this directly. I'm going to be discussing now an even simpler formulation for this. Hopefully you can see the connection with the minimum cost flow problem. Then the bin packing problem, job shop scheduling and flow shop scheduling problem, and airplane hopping problem. Okay, so assignment problem. So in this case, we're going to have a set of workers and a set of jobs. And for that particular instance, the idea is that you want to assign a worker to a job. Okay, that's really important. And for this basic structure of the assignment problem, you're going to assume that the number of workers and the number of jobs is going to be balanced, so pretty much the same number. That way, you're going to assign exactly one worker to exactly one job and exactly one job to each of the workers. So what are my parameters going to be? You're going to have a cost of assigning the worker. Now, this depends actually on the context. In some contexts, you may have a cost of doing the assignment. Let's say that you're a surgeon, you're assigning surgeons to different surgeries, and each of those surgeons is going to have a different cost for the surgeries. So you would like to minimize the cost. Let's say that's the case. Of course, assuming that all of them are qualified to do the jobs, right? So if that's the case, you would like to just find out what is the minimum cost. Now, in some other cases, let's say that again, you're looking at the surgeries, you may say, well, I actually don't care that much about the cost. I want to make sure that I assign the surgeons based on their specialties. That way, I have more confidence that the surgeon is going to do a better job. So now, instead of a cost, you may have a parameter related to the preference. Okay, and the difference here is going to be that if you're going to take into account the costs, you want to minimize the total cost. But if you're going to, if you want to take into account the preferences, you would like to maximize the average preference assignment that you do. Okay, so what is the objective function? If you look at cost again, minimizing the total assignment cost, while guaranteeing that each worker has one job and one job has exactly one worker assigned. So how do we model this? So let me actually put this example to showcase what we're discussing. So let's say that you have here five people, right? So 5 persons here and 5 projects. And we would like to assign each person to a project. And in this case, let's say that what I want to do actually is maximize my total preference. So I would do a survey asking each of the persons, what is their preference with respect to each of the jobs that are available? So I'm going to ask them, what is your preference? Please put 1 if it's the lowest preference and 5 if it's the highest preference. And they would rank the jobs. That's the idea. So after they have ranked them, so this is the solution that you have. So pretty much for each person and each job, this is the preference that they gave. So you have all that information all together. And now the idea is to actually assign all the projects to the people that you have at hand, so that the total assignment, let's say preference, the associated preferences, the aggregation of that is maximum. So the solution for this particular problem would be this one right here. So if you were to look at what jobs were assigned to which people, and you look at their preference and then sum all those preferences, the sum in this particular case would be 21. This would be a maximum preference possible. Okay. How do we actually model this now? So in this particular case, you had set of workers, right? Set of jobs. The parameters here, as I mentioned, this is general here. So you could have a cost of assigning the worker to a job or a preference. The variable here is a binary variable that is going to be 1 if the worker is assigned to a job and 0 otherwise, okay? Where I is associated to a worker and j is associated to a job. So the objective function, as I mentioned, if you want to minimize cost, then you simply minimize this double sum here over workers and over jobs. If you want to maximize preference, you would be maximize this sum right here. That's the only difference. Okay? What are the constraints? As I mentioned, you want to make sure that for every single job, the sum over all workers. So you look at each job and you see that job to which people were it was assigned. And you will look at every single person and the sum of the assignments has to be exactly 1. That means that you can assign only once that job. If you do the same process now for the workers, then literally you're going to take every single worker and you see how many jobs were assigned to that worker. And you need to make sure that that number is exactly one, because you have to assign only one job to each of the persons in your list. Okay, so this will be your optimization model in this case. Bin packing problem. So in this case, the problem that you have at hand is you have multiple bins, right? And then you have multiple items and you would like to assign items to those bins. So it looks like an assignment problem to some extent. The difference here is that it's not a one-to-one assignment, right? So you're going to have large bins that most likely are going to be able to have multiple items at the same time. Okay? So in this particular case, what you want to decide is from your different bins, you want to know which ones you want to use. And also you want to know which items you're going to be assigning to the bins that you're going to be using. Okay? So the sets in my problem here are going to be a set of bins that I have, and you're going to have a set of items as well. And the parameters that you're going to take into account are the size of the item. So each of the items is going to have a different size. This indicates that maybe in some cases, for some bins, you may not be able to allocate some items. Okay, so it's important to keep this in mind. Of course, you need to know the capacity of each of the bins. Okay, so, and as I just mentioned, the objective here would be determining the packing strategy that minimizes the total number of bins used. Okay, so assume that every time you use a bin, you have to pay a fixed amount. Okay, so you would like to use as few bins as possible while packing all the items in your set. So what are going to be my decision variables? You're going to have one binary variable that indicates if the item I is packed in bin B. Okay, so with 1, if you're packing that item in that bin, 0 if not. And you're going to have another binary variable that is going to be indicating if you're going to be using or purchasing a bin or not. Okay, so what is going to be your formulation? The objective function, as I mentioned, is going to be minimizing the total number of bins that you use. So that is as simple as literally summing all the binary variables associated with your bins and minimizing that. I want to make a note here that if you have different costs associated with each of the bins, then the only thing that you will need to do is pre-multiply this binary by the cost. Okay, so let's call a cost for each bin B. So that will minimize the total cost here. Now the constraints that you're going to have. So for one, hopefully you're going to see that this is similar to the network design problem that we just discussed. This constraint is saying, well, I need to make sure that the total number of items that I'm packing doesn't exceed the capacity of the bin, right? So what do you need to know? In one hand, here to the left, this will be calculating the total size used by all the items that you're packing in bin B. Okay, so remember that X tells you which bins you pack, which items you pack in bin B, and S sub I is the size of those items. So whenever you sum all of that over your items, that's going to tell you a total size that you have to use. And in the right side, this here is going to be the capacity of the bin, of course, taking into account if you actually pay to use that bin or not. If you decide not to pay for that bin, so this Y is going to be 0, so all of this will become 0. But if you actually decide to use that bin, so that Y instead would take a value of 1, so at the end, you will end up with the capacity of the bin. Okay? The second constraint listed is simply saying that if you look at all your items, so for every single item, right? So for all items in my set of items, if you sum all the bins, if you look at every single bin, that has to be packed somewhere, okay? And not only that, it has to be packed exactly once, okay? So this is telling me that all the items are packed exactly once in one of the bins. And here is what we call the nature of the variables. saying that this X is going to be a binary variable, so they can take only 0 or 1 values, and the same for Y. So for that particular example that I mentioned, so the example, you have 20 items, and each of those has different sizes. And your bins, you have 11 bins that you could use with different capacities. And you're wondering how to assign them. So this would be a solution. You're going to be using only 9 bins. So in this particular case, you're going to be using bin 4 or bin 9. Now let's talk about job shop scaling problem. So in this case, what we have is, let's say that you're producing some type of product, right? And the idea is that you need to make sure that whenever you're making those products, right, you know what is the sequence that you have to have with respect to different machines. Okay? And you may actually have different jobs. Okay? So that's why the name job shop. So the jobs, each of the jobs may have a different sequence. And sequence here is determined by which machines you're going to be using and in which order. Okay, so for example, here, let's say you have only 3 jobs to do. Okay, let's say you produce 3 types of products, so each of those is going to be a different job. So for job 1, the sequence is 1, 3, and then the 0 at the end means that you don't have to do anything else. So in order to complete job 1, you need to send it first to machine 1, then to machine 3, and that's it. Okay, but then for job 2, the sequence is going to machine 2 first, then machine 1, and then machine 3. And for job 3, you need to start with machine 3, then machine 1, and then machine 2. Okay? Now here the important thing to know, not only a sequence, but also the duration that you're going to have. So you're going to have, for each machine, each job is going to have different durations. So let's say these are the durations associated with that. Okay. So in that information, what do you want to know? What do you want to decide? You want to find out what is the best configuration to have so that the total time that you will take to process all your jobs is minimum. Okay. So what are going to be my constraints and in general my mathematical formulation here? So the sets, first of all, my sets are going to be 3. So one is the set of machines. Of course, you need to know which machines you're going to be using. Second is the set of jobs. So you need to know which jobs you're going to be assigning. And then, of course, you need to have some set of ranks or processing order, pretty much the sequences that we just discussed. Now, the parameters are going to be the duration of the jobs in each of the machines. Okay. And here, the second one, the QJS, is the machine order rank for each of the jobs. Okay, so this is going to be pretty much the parameter that is going to be telling me for each of my my machines the ranking or the position in my scale. That's it. So what is the objective here? Determining, again, the job scaling that would minimize the total completion time. So now let's actually look at the different decision variables that you will have. So here you're going to have a decision variable T that tells you a start time of job J in machine M. Okay, so that's the first decision variable. Second one, as you may imagine, is now the end time of that job J in machine M. Third one is what we're going to be calling an auxiliary variable. And this, what it's going to be doing is going to be associated with the largest end time. Okay, so it's going to be Z. And then finally, we're going to have a variable W that is going to be indicating if job J1 is processed before job J2 in machine M. Okay, so it's really important in this particular case to know which job is done before the other job in each of the machines. Okay, so you take job J1 and job J2. You need to know in your decision, right, in your solution at the end, you need to know which one was first. Was it this one or was it this one? So that's the decision variable that is indicating here. And of course, that depends on the machine. Okay, so what is my objective function? As I mentioned, we have decision variable z that was an auxiliary variable that was constructed just to measure the largest end time. So what do you want to minimize? That maximum end time, right? You want to make sure that you minimize the largest end times from all the jobs. So what are my constraints? So for one, of course, a constraint that connects the start time with the end time. How do you do that? Well, simply you know that the end time is going to be start time plus the duration of that job in that machine. Okay. Second thing that you need to make sure is that the auxiliary variable z is greater or equal than all the end times. So if you look at every single job, that variable z, the auxiliary variable, has to be greater than every single end time for all the jobs. Okay. This is this constraint right here. So what else are we going to have here? Now, depending precisely on the different orders from the sequences, you need to make sure that the start time of a given job in a given machine is greater than the end time of the same job in the previous machine. Okay, so here, just so that you don't get confused, you're looking at J, so that is a specific job, and then what is this Q? What you're saying is, oh, okay, I take my Q of JS, that means the position of my job, right? J in my scale, right? And then you look at the position of the same job, but in the next order in my scale. So the only thing I'm saying here, and if we want to go back, let me just go back here to these constraints. The only thing that I'm saying is that the end time for job one, associated with my machine 3 has to be, sorry, the start time associated with my machine 3 has to be greater than the end time of the same job whenever it was processed in my machine 1. Okay, because remember here what this sequence says is that you need to go to machine 1 first and then to machine 3, and that's it, right? So I need to make sure that the start time in machine 3 is greater than the end time in the previous station, the previous machine. That's what this is saying. Okay. Now, these two are going to be a little bit trickier. So, but still, I'm going to explain this to you to have a sense of what is going on. Now, here, depending on which one was first, J1 or J2 in a machine M, right? So you're looking at a machine M and you look at the two jobs, J1 and J2, and depending on which one was first, then you would say, oh, okay, if J1 happens first, happens before J2, what would that mean? Well, immediately would say, well, since this is first, that means that the end time of J1 has to be before the start time of J2, right? Because J1 was first and J2 was afterward, right? But if it's the other way around, if J2 actually is the first one that is completed, so whenever you look at these two, so if this is before J1, then the end time of J2 has to be less than the end time, that the start time of J1. That's it. Okay, so this, what is this going? You're guaranteeing that you're not going to have overlapping jobs in the same machine. Okay, and that's why it's so important to have this parameter, this variable, sorry, W. Okay, so depending which one was first, you're going to make sure that the end time of one job and the start time of the following one actually makes sense. Okay. And this precisely is, these two constraints are exactly doing what I just mentioned. If this is first, meaning that this is 1, right? Then this is going to happen, right? But if this one was the first one, then this is going to become 0, so nothing happens. And then this is the one that is going to take place. Okay, so now you're making sure that you're connecting the end time of one job with the start time of the other. Okay, and that was it. Here simply now remains the decision of the nature of the variables. So of course the times, the end time and the starting time are going to be simply continuous variables. The completion time, the total completion time is going to be also continuous, but then you need that binary variable that indicates for each machine which job was first compared to another job. So in other words, this variable that is taking is every single pair of jobs in each machine and is telling me if the first or the second in that pair that I'm looking at were the first. Okay, which one is the first? Okay, so if you use that formulation to solve this problem, exactly one I just mentioned, so the result would be this one with a completion time of 97. So as you can see, so what this is saying is, yeah, okay, start with job 2 in machine 2, and as soon as it finishes, then it will go to machine 1, and as soon as it finishes, it will go to machine 3. Okay, and at the same time here, whenever you start that job 2, you're going to start job 3 in machine 3, and as soon as it finishes, it's going to go to this machine, but it's going to have to wait a little bit because the job that was there is still being processed, so you have to wait until it finishes. Now you go here, and as soon as you finish, you will jump to this one. Okay, so important thing here to keep in mind, of course, is that you're going to have some idle times for some machines. That's precisely what you would like to avoid as much as possible, but some cases you always are, in general, you're always going to have some idle time no matter what. Okay, so flow shop scheduling. So this is going to be very similar to what we just did for the job shop. In this case, the assumption is going to be that all the sequences are fixed. So you know the sequence for all of them, and they're going to be the same. And now we want to literally do the same assignment process, but assuming that all the sequences are simply in the same order for all the jobs. So I started with the job shop scaling problem because we can use that formulation now to solve the flow shop. How is that? Well, as I mentioned, the sequences are going to be the same, so you can use exactly the same sequence in all of them, and then you use the same formulation that we had from before. So in this case, precisely a sequence for every job is going from machine 1 to machine 2 to machine 3. That's the sequence that we would use in the formulation from before. And then this problem, in this case, let's say you have 3 machines and 6 jobs that you need to process. And as I mentioned, each job has to go first through machine 1, then machine 2, and then machine 3. You know the durations of all of them. And then you need to determine in which order you're going to process your jobs. So the optimal solution for this case is starting with job 1, then you follow with job 4, then job 6, then job 5, then job 3, and then job 2. Now we have the TSP problem. So this is very common. You're going to, I'm sure you have seen this quite often. So the idea of this traveling salesperson problem is that you are going to have a set of nodes to visit. Right? You start from a given node in your network. You want to go around your network and visit all the nodes exactly once, and then go back to the node of origin. So in this case, again, the sets are going to be simply the ones associated with the network that you're studying. So a set of nodes and a set of arcs. You're going to have as a parameter the cost of traveling through each of the arcs, because the idea here is to do all that route at minimum cost. So imagine here that you have to pay for airplanes and you want to go from, like, you're traveling in Europe and you're planning for different, to visit a set of 10 cities, let's say, but you don't know in which order you should visit them, because depending on what flights you decide to buy, the cost is going to be different. So that will be precisely that parameter here. Now imagine that you're here in Norman and you need to go to 5 different places today, but you need to make sure that the time that you spend traveling is the least amount of time possible, so that parameter, that cost, is actually going to be the time that it takes to go from one node to a different node, or from one location to another. So at the end, you will be finding out what is like for that particular context, you will be finding the shortest route that will take you to go through all the places that you needed to go. Okay. So let's look at this example right here. We're going to have these 7 cities, and you want to go around all of them. assume that you have the distances between the cities. Let's say that that's what we care of right now. So we're going to have a matrix of distances. And I'm giving you also the positions here, but really what you care is about the actual distances in between the cities. So you want to determine the best route. Something I want to point out here is that for a problem like this, where you can actually see, this may look simple actually, so you may be able to find a good route for this just by looking at it. But in general, this problem gets extremely complicated whenever you increase the size of the network. Okay? So the optimal solution for this one, probably you would have guessed just by trying it, just by trying to draw it, would be this one right here. So you start, let's say, from node 1, right? If it's undirected, it's important to mention this. If the network is undirected, it doesn't matter the direction that you take for the route. So you could go 1, 5, and then 2, 6, and then 2, and so on, right? Or you could go the very opposite direction and it will be identical. But if the network is directed, meaning that that you really are going to take into account, I mean, it does matter if you go in this direction or in the opposite direction. You need to look at which arcs you can travel, and also the cost associated with which direction. Okay. Now, what is going to be a formulation for this? As I mentioned, this problem is really difficult in general. So it's not difficult to formulate per se, but it's difficult to formulate it in a very efficient way, actually. And it's still a problem that is under research even today. But fortunately, we can solve very, very large problems nowadays thanks to the computational power and the algorithms that we have nowadays. But for let's say for your basic, let's say needs, let's say at least a starting point, you could use a formulation like the one I'm just going to explain. So first, the sets are going to be exactly the same as before, set of nodes and an arc and the set of arcs. So pretty much you have a network, and then a parameter associated with the cost of traveling through each of the arcs. So in this case, what are going to be my variables? You're going to have a variable that tells you if you're going to travel from one city to another one. So meaning you're going to travel through the arc or not. Okay, so one, if you actually go from one city to a different city, and 0 otherwise. Okay, so let's say you're talking about going in Europe. So that variable will be 1 if you decide to fly directly from Paris to let's say Venice, and 0 if you don't travel using that direct flight. Okay? You need another variable for this particular formulation, and it's called U, which is a label or order of visit of each node. Okay? And this is done to eliminate subtours, and I'm going to be discussing this in a second. So the objective function, as you can imagine, is minimizing the cost, the sum of the cost times those binary variables. So that would be a total cost, right, of your entire tour. What are the constraints? Well, you need to make sure that you're going to be entering each node at least once. So if you go, literally, you're looking at node J. So for every J, for every node or city J, you're going to look at every single city that can go to J, and you're going to sum that variable, that binary variable. It has to be exactly 1. So that will be telling me that if you're in a node J and you look at all the other cities that could be the origin city, exactly 1 has to be the origin city. You have to have arrived from somewhere. And analogously, if you take any city and you now sum over all the possible following cities, you have to have exactly a sum of 1, meaning you have to go to a city for sure after you visited node I, okay, to a different city or a different node. Now here, this constraint, what it's going to be doing is again connecting let's say the dots regarding the order of the visits. So here what we're saying is, since U is going to be a label or the order of the visit for each of the nodes, so you're going to have 2 cases. One, if U sub I is greater than U sub J. So what does that mean? that node I was visited after node J. Okay. Now, if you change this and you say that U of I was less than U sub J, that would mean that you visited node I before node J. Okay, so based on that, you're going to write then this constraint. So if, let's say for a second that UI is actually less than UJ, so what is that going to happen? Or when can that happen? I think it's easier to see it that way. Let's look at the binary. So if the binary xij is equal to 1 at some point, what does that mean? If this is 1, it means immediately that the label associated with the node I is exactly 1 unit less than the label of j, right? And in general, what I'm saying is that ui is less than uj, right? That's what it would be. Now, if this is 0, you really don't have to put any constraint. So that's pretty much what we're going to be doing here. We really care is whenever you have a 1, you need to make sure that those two labels are actually making sense. So if this is 1, if xij is 1, then this here would be 1. So this entire thing would be 0. So this entire product would disappear. And at the end, what you're saying is, oh, okay, u sub I has to be less than or equal to u sub j minus 1. Right? You see? So that's precisely, we have this less than or equal to, less than, sorry. So whenever you put the equality, you would say this. So what is this saying? Well, literally it's simply saying, well, since I visited node I first and then I went to j, that's what this variable is saying, then the label of I has to be at most the label of the following city minus 1. That's it. Okay. And finally, well, the nature of the variables, you're going to have that x is a binary variable, so 0, 1, and u is going to be pretty much a continuous variable. So at least 0, okay? But it could take any continuous value. Now let's look at this example. So what happens is that the formulation that I just described, it may really not scale that well because it has that binary constraint. And I really would recommend you to try it. So whenever we look at these problems, even if you have a problem with, let's say, six nodes, if you try to do that in Solver in Excel, that may actually get stuck. See, so it's actually quite complex, even though it seems very simple. So now imagine you have a larger network, like the network of different cities in the US. Let's say that you wanted to visit all of the cities in the US at minimum cost, right? So how will you do it? Well, you could try to solve that formulation that I gave you. If you're using a relatively good computer, you should be able to solve it, but it may take some time, right? And so there's another approach also that is using iterative cuts. So what does it do? So probably you have been thinking from the beginning, why the heck didn't we use simply the shortest path, right? So I'm going to show you in a second why we didn't use the shortest path. So the thing is that you're going to have your different nodes. Let's say that let's say that you start from this city. Okay, let's say that this is your starting city. And what you're going to do, trying to build a fictitious shortest path, that is, yeah, you're going to model it as you want to find the shortest path from this node to a copy of the node right on top of it, right? So it's a fictitious city that would be literally in the same location. And you want to have the path from that city to itself, pretty much to that mirror location. And you would have to add a constraint, right? In that case, that tells you that you're visiting all the cities. Otherwise, the shortest path would be 0. You're just going from the city to a mirror city. So you're just staying there. But then if you add a constraint saying that every single city is visited exactly once, you may think, yeah, that should work, right? So let's look at what will happen. So if you solve that, what is going to happen is that you're going to have what we call subtours. Okay, so that's really an issue. So why is that? Well, if you think about it, if you start from a city, let's say this one was the starting city. Well, the city is leading to a different city, then here and then back. And that's it, right? So you would say, yeah, I actually did a tour, right? But I didn't visit all the cities, right? So mathematically, what is going to happen in the computer is that it's going to find a solution that mathematically would still follow all the constraints that you have indicated. And is that for the others, you're going to have some tours, right? So in theory, all those cities are going to be visited, but the issue is that those tours were not connected to the main tour. And if you think about it, it is extremely difficult to actually make sure that that happens. Like, think about it that way. If you're in a city and you know where you came from and you know where you're going to, there's no possible way to know what happened 10 cities ago. Or if you actually are going to go uh, to another city of interest in 10 periods in the future, right? It's really not easy to know that, to have that information. So to model that is really not that easy. So what can we do? Well, you would simply solve the shortest path as usual. But once you have solved that, then you're going to have some algorithm to actually visit. Let's say you start from here and you would jump from city, the next city, the next city, and next city. And if you went back and you didn't visit all your cities, that means necessarily that you had subtours in your problem. So you would have to add a constraint that would eliminate subtours. How do we do that? Let me give you an example. Let's take these 3 nodes here, those form a subtour. So let's say that the names here of those 3 cities, let me label them just for simplicity. Let's say that those are called A, B, and C. Okay. So here, immediately, you know that if that tour exists, is because X, A, and B, X, B, and C, and X, C to A, all of them were 1. Or if you go in the opposite direction, literally XBA, XCB, and XAC, all of them were 1. So meaning either you went in this direction or the opposite, right? So that is a subtour, right? That's literally a subtour. You're only visiting those 3 cities. How can we eliminate that subtour mathematically? Well, you have to add the following constraints. For this subtour, since you know that for the subtour to exist, all of these have to be 1. What you could say is simply, okay, let's take those variables from the solution that you just obtained and sum them. And if you now say that that's less than or equal to the number of arcs in that subtour minus 1, so that would be 3 minus 1, so 2, right? Immediately, what it's saying is that out of those 3 arcs, you can only be using 2. You cannot use the 3 of them. Okay, so that's literally what is going to happen. And of course, you have to take into account the other direction. Okay, so by doing these constraints, you're going to eliminate the subtour. This subtour will never be able to happen again. And then you will have to replicate the same idea for every single subtour that you observe. You take every single subtour and you repeat that. You add those constraints. So once you add those constraints, so for example, in this case, you have 28 subtours. You add those constraints this way I'm explaining, and then you solve again your shortest path with those new constraints. And then you're going to have a different solution now that has, again, subtours, but different subtours. Okay, so in this case, you reduce the number of subtours from 28 to 22. So what happens? You need to now solve again the shortest path with the constraints that you're visiting all the cities and the constraints from the previous subtours that you had eliminated, and also eliminating the new subtours that just came out. So this one, all of them, pretty much all of them. So you're literally going to be accumulating constraints. So from iteration 1, all the subtours, and now in this iteration, all the subtours from the previous one and all the subtours from here, and you repeat that process. And now you're going to end up with 10 subtours. So now you need to solve again taking into account the subtours that were in iteration 1 and the ones in iteration 2 and the ones in this iteration 3. You repeat that process again and again and again, and you keep going until you find a solution with only one tour. If you get to a solution with only one tour, and again, remember, how do we know? You take your city and you start actually just following the solution. And if you come back, you check which cities you visited. If you visited all the cities just with one tour, then you're in the optimal solution. And this is guaranteed to be the shortest path possible for that cycle. Okay, so that would be a solution to that trial incident problem. Okay, I hope that was really insightful to you. I'll be sure to be posting all the mathematical codes or the codes for this in Python for you to have a look at them and know how to solve these problems. I hope you enjoyed the class and have a good day.